Hi, let's talk about capillary exchange this time. Hopefully you're rested, had a little caffeine, and we'll just start in on this. So for capillary exchange, we've already kind of gone over this basic idea. This is the blood flow on the right, and this is the interstitial fluid. It's just the exchange back and forth across the capillary wall. The forces that we're going to be looking at are hydrostatic pressure, which is essentially fluid pressure, and it's highest in the blood vessels, so it's literally pushing the blood, not the blood, but the fluid, the plasma, or the liquid portion of the plasma out through the pores of the capillary, and then osmotic pressure within the blood is drawing it back in. So forces out plus and the forces in are what we're going to be looking at. So it's that exchange of fluid. On a sort of a larger conceptual picture on the right, here is a capillary bed with an arteriole and a venule and a capillary across the two. And what we see is net filtration. At the arterial end, the fluid is going out into the interstitial fluid, those interstitial spaces. And then at the venule end of the capillary, the fluid is being returned. So there's this exchange out in the ISF. That's what we're going to be looking at, is the filtration and the reabsorption. So a couple of things to review. You see the pressure curve. We've looked at this several times, so you're familiar with that. And the fluid is pushed out at the arterial end. So I'm going to talk in terms of push and pull. So fluid is pushed out at the arterial end of the capillary where the pressure is higher. And the fluid will be pulled back in at the venule end by osmosis, where the pressure is lower. So that's what's going to be changing across the capillary bed, is the hydrostatic or the blood pressure. The osmotic pressure, you need to pay attention to this, it's constant across the capillary, so that does not change. And the osmotic pressure is determined primarily by colloids in the blood. These are large particles. In particular, we're talking about albumins. And these are proteins, serum plasma proteins, that are made in the liver. Assuming that the liver is functioning normally. If we have liver disease, the albumin proteins are going to be down, and then we will have reduced osmotic pressure. If the liver is failing, remember that it also is responsible for clotting proteins, so it's likely that the patient would have blood clotting disorders. They might be more prone to hematomas or bruising. They present with multiple bruises that are unexplainable. So back to the albumins and these osmotic proteins. These are large proteins that are too large to leak out of these continuous capillaries. So the point is that the albumins stay in the plasma. Now, when we're talking about osmosis here, it's a little bit different than what we've talked about in the past in Biology 160 or earlier, when we were primarily looking at sodium. And previously, we were looking at osmosis across the cell membrane. which is impermeable to sodium. But in the capillary walls, they are permeable. They have holes in them. So these are continuous capillaries that allow all of the small stuff, including ions, sodium, potassium, etc., and small molecules like glucose, to readily diffuse out of the blood vessels. And it's all done down a gradient. So the serum albumins, the plasma albumins, these large proteins, cannot escape the blood. They stay in the blood and confer this osmotic potential or this osmotic pressure to the blood. So the key points here in this story of capillary exchange is that the blood pressure is higher than osmotic pressure at the arterial end. So with the blood pressure being higher, the push being greater than the pull back in, fluid is pushed out at the arterial end. At the venual end, the osmotic pressure is the same, but the blood pressure has dropped. So the osmotic pressure now is higher than the blood pressure, and the fluid is pulled back in. And that's what's shown essentially on this figure at the right. The capillary blood pressure is high, and that forces the fluid out at the arterial end. At the venual end, the blood pressure has dropped. The osmotic pressure is still the same, and blood, or fluid, I shouldn't say blood, but interstitial fluid, or the fluid is then drawn back into the venual end. A small amount of the fluid normally that is not reabsorbed, because generally filtration is greater than reabsorption, some of that excess fluid leaks into the lymphatic system. And then that travels, remember how that goes? That goes back through the lymphatic system and is ultimately returned to the blood vessels in the plasma. So this is the story that we're going to be looking at. So let's go through the notes on the right first. It's sort of the alphabet soup of abbreviations. Hydrostatic pressure and blood pressure, they're both fluid pressures. So we'll just stick with hydrostatic pressure so that we don't have to distinguish between plasma and pressure and interstitial fluid pressure. We'll just talk about fluid pressure in general as hydrostatic. We could be in the blood or we could be in the interstitial spaces. So that's our HP, our hydrostatic pressure. And we have hydrostatic pressure in the capillary. That's our blood pressure. And we also may have hydrostatic pressure in the interstitial fluid, which we'll just abbreviate as HP sub ISF. And this is the fluid that if it builds up, we wind up with swelling, edema. Okay, the osmotic pressure in the capillary, OP the sub C, that was determined by the albumins in the blood. They stay in the capillary, and this is constant, normally, as we'll see. Hope that didn't run off the screen. And we can also have osmotic pressure in the interstitial fluid. If some protein leaks out of the blood into the ISF, it can give that fluid compartment a little bit of osmotic pull. So I think that it's helpful to initially think of blood pressure or hydrostatic pressure as pushing and osmotic pressure as pulling. And the units are all millimeters of mercury, whether we write them or not. But if I ask you to calculate a net filtration pressure, your units should be millimeters of mercury. So let's run through this. So what we're going to be looking at, here's the basic formula. This is how I like to think about it. I think it's easiest. We want the net, the overall filtration pressure. And we're going to do that at both the arterial end, and then we're going to calculate it again for the venule end of the capillary. And I've divided the capillary up in the figure on the slide, the left and the right. And what's shown is the arterial end of the capillary. We'll do that first, and then we'll come back and do the venule end of the capillary. But the math is exactly the same. So what we're going to be looking at, if you think in terms of forces out minus forces in. So what are the forces that are making fluid leave the capillary, and what are the forces bringing it back in? That's the idea. So the forces out are drawn with the little blue arrows. This one is not blue. So what do we have? We have hydrostatic pressure in the capillary as 35. So this, you could, if you want to, write this in, although it gets pretty crowded pretty quick. Hydrostatic pressure in the capillary is 35 millimeters of mercury. That's the blood pressure that's pushing it out. And what else could be drawing it out? Well, we could have some osmotic pressure in the interstitial fluid. There could be some protein out here in the ISF. Let's pretend that that's 1. So our force is out. We'll calculate that again in the next slide. So the forces in that we're looking at are the osmotic pressure in the capillary and a little bit of push from the ISF. So here we have osmotic pressure in the capillary pulling fluid back in at 26 millimeters of mercury. We could also have a little bit of fluid pressure out in the interstitial fluid, perhaps from edema, swelling, but for right now let's just pretend it's 0. So the forces out would be, the total of those would be 26 plus 0. Let's go to the next slide and crunch the numbers. Okay. So, same thing that we had on the other slide. Net filtration pressure is the difference between forces out and forces in. So we're going to calculate all the forces out. And so what do we have over here on the right? The net filtration pressure, remember we're doing this at the arterial end right now. So there's 35 plus 1. These are the forces out. Make sure you know where these are coming from. The 35 is our hydrostatic pressure in the capillary pushing blood out. And the 1 comes from a little bit of osmotic pull. So we're adding those together, the 35 plus the 1, forcing water out, and then subtract the total of forces in, which we had 26 osmotic pressure in the capillary, and there was 0 push from the hydrostatic fluid in the interstitial fluid, so that's 0. So we have 36 minus 26. The net filtration pressure at the arterial end is 10 millimeters of mercury. So there's more flowing out at the arterial end than is flowing back in. That's the net pressure. More going out than returning. Okay, let's do the venule end in the next slide. So we're doing exactly the same thing to calculate the net filtration pressure now at the venule end of the capillary. Notice that the only term that has changed in the story is the hydrostatic pressure. And that makes sense. So the hydrostatic pressure is the only term that changed. The osmotic pressure in the interstitial fluid, that's the same over here on the venule side as it is over here. It's all interstitial fluid. And the osmotic pressure hasn't changed because the albumins didn't go anywhere. So it was osmotic pressure in the capillary was 26 on the arterial side. Proteins flow to the venule side, it's the same, 26. And we didn't change any of the proteins out in the interstitial fluid, so that's also 0. So we add up the forces out, which are the 16, that's our hydrostatic pressure, and 1 for osmotic pull in the ISF, that gives us 17, and then it's still 26 plus 0, so we have 17 minus 26, the difference is minus 9. So there is our net filtration pressure at the venule end. So it's a negative pressure. On the arterial side, it was a positive pressure, forcing it out. On the venule side, it's a negative pressure, drawing fluid back in. And that's how we get our exchange. Flows out at the arterial side, flows back in at the venule side. The next slide is a chance for you to practice. So you can print out several copies of this, or one copy, do it in pencil, and then just practice. Because what I may do is just give you some numbers and have you calculate the net filtration pressure at either the arterial end or at the venule end of the capillary. So let's do an example. So let me just say here, practice this. It's not a difficult concept, you just need to do it. And if you get it down now, that'll be good, because we're going to be doing essentially the same thing a couple other places in the course. When we get to the kidneys, we will calculate net filtration pressure at the glomerulus of the kidney. And if you understand it here, when we get to the kidneys, it'll be no trouble at all. So let's pretend that I give you, I'll just give you some numbers, and let's calculate the net filtration pressure at the arterial end, and then you can do it at the venule end. So the idea here is just to make up some numbers. Make something reasonable. You might start with what I gave you on the previous slide and then tweak it slightly. So for example, let's say, let's get a smaller pen. So for example, let's say I'm up at the top left corner of the screen. Let's set the hydrostatic pressure in the capillary at 30. Again, all of these numbers are millimeters of mercury. And let's set the osmotic pressure in the capillary at 24. I'm just kind of making these numbers up, but they're close to what we had before. And let's do the interstitial fluid. So that's the capillary side compartment. And let's do the hydrostatic pressure in the ISF. And let's make that 1. And let's make an osmotic pressure in the ISF. And let's set that to 1 also. And then let's calculate the net filtration pressure at the arterial end. So we can plug the numbers in here if we want. So here we have hydrostatic pressure in the capillary as 30. And we have the osmotic pressure in the capillary as 24. Okay. And we have the hydrostatic pressure in the ISF at 1, and the osmotic pressure in the ISF equal to 1. Okay, so you know our formula, net filtration pressure, and here we're at the arterial end, equals our forces out, the sum of those forces out, minus the sum of the forces in. So we just put the numbers in. And out is the 30 and the osmotic draw in the interstitial fluid. So we have 30 plus 1 minus what's drawing the fluid back in. The osmotic pressure of the capillary, which is 24, plus any push from the hydrostatic fluid, which is also 1. So our net filtration pressure is 31 minus 25. And 31, that would be 6, right? 6 and 25. So 6 millimeters of mercury. That is our NFP at the arterial end. So you should do the same thing at the venule end. So let me give you some numbers to practice. So now let's say the hydrostatic pressure in the capillary is going to be less. Keep it reasonable. It's dropped from 30, let's say, to 17. And our osmotic pressure in the capillary should still be the same. So that's 24. And then the hydrostatic pressure in the interstitial fluid, so we'll do that fluid compartment now, is 1, same as it was before, and the osmotic pressure in the ISF also hasn't changed. It's 1. So then you calculate the net filtration pressure at the venule end of the capillary. And please ask if you have questions. So that's it for this time. And we'll see you shortly for another lecture on blood pressure and flow.